Good evening, everyone. My name is Rohit. I am part of the binary exploitation team. I shall be taking the training session for binary exploitation. So, we'll see what is binary exploitation. So, it is essentially exploiting software for fun and profit. For ease of saying, we'll say it's just hacking software for fun and profit. Okay, so we'll be covering these following things, which are the introduction to like binary exploitation, why we do it, and what are binaries and things like that. Then how are binaries earned? Then syscalls, where we look at uh, how the library functions interact with syscalls to do their tasks. Then we look briefly into stack, and then finally solve a challenge, which is a red to win challenge. Okay, so what is a binary? So binary is essentially a compiled program that runs on your computer. So if you have a C code and then you compile it, it would essentially initially be converted to an intermediate language, then to a .s file, which is assembly. Then the assembler would convert it to a set of objects files, and then finally the linker links it. So all of this happens in one stretch using like GCC, this command. Uh, I shall demonstrate. Okay, so uh, this is an error that is because of truncated function in the C library. We shall be looking at this later while our demo is going to be taking place. So you can avoid this by adding a implicit function declaration uh, flag. So yeah, after that you will get a file ABC. Here that file is essentially challenge. So you can see that the green things are essentially mean that they are executable. So if you want to run the challenge, you can just run it like this. So that's essentially how a compilation works. Uh, and this is the code that we just compiled. We'll look into it briefly later on. Now we'll get back to the slides. So if you do file on the compile program, you'll see that it's an ELF 64-bit usually, and LSB Pi executable. So these are certain Pi is essentially few mitigations and features that are added to strengthen the binary so that people like us don't exploit the binary that easily. So yeah, binary essentially just programs that run on your PC. You can make it if you compile C code or C++ code, and that's it. Now, what is exploitation though? I alias the word exploitation with hacking, but then, yeah, in simple terms, exploitation is just using the bugs in the program to do things that the program wasn't made for. So suppose a very simple example, you have a cooler in your house. So suddenly your cooler turns into a heater. That would be an issue, right? So uh, this is a very simple hardware example, but then like in software, the things that you can do are extremely creative. So yes, suppose we have a program like this, and then what you are trying to do is just declaring a buffer of size 30, getting data into the buffer. So what a buffer is, it's just a storage space that you declare, and then you are printing the buffer with hello percentages. So it will print hello and whatever you give into the buffer. So that essentially is an issue because here we can see that mm, gets is a function that allows the user to take in how much ever input uh, that you can give into. So this is an issue. We'll get to it in the coming slides. So this is essentially one kind of bug in programming perspective. So I said what are binaries? Now where are the binaries? As in what all are the binaries that we see in daily life? That we can see here. Uh, so yeah, this is the compilers GCC clangd. This is the logo of GCC. Pretty cool, if uh, I say so myself. Then there is Chrome, Firefox, which are like browsers. You have the kernel itself, which can be represented as a binary. Then you have like your terminal binaries such as gnome, tmux, etc. Then you have your code editors. All of these are just binaries. So binaries are all around us. So when you learn binary exploitation, you are essentially learning the art of hacking programs such as these. Also, in a very brief manner, we are discussing like what is, why do we actually exploit binaries? So we find a bug in a program, exploit the binary, then report it to like authorities or like authors of the program, so that like you can possibly gain rewards and make the program more secure. So this is essentially a very simple workflow that people who do binary exploitation in a professional setting do. So we discussed about binaries, but then how are they run? So what I did just now was dot slash abc. So what exactly happens when you do dot slash abc? So the operating system transfers control to the loader. So essentially, if you do this command, ldd challenge, you can see the loader as lib64 ld linux x86 64 so.2. So this is essentially the loader that loads your program into memory. This happens when you do this command in the terminal. So after that, the loader loads binary into memory. After that, loader gets the library files related to it. So when you see this command, you can see that libc.so.6 is the glibc that the challenge is depending on. So we'll get to what a library is in a second. Then the loader transfers control to the binary. So it essentially runs the binary. So what are libraries though? I told about libraries. Libraries are essentially binaries that exist within the system, which allow us to use certain functions that are not specifically written by us. So it is essentially to reduce the complexity of code that we write. So in a way that it also prevents you from adding the same piece of code into every single program when it's not necessarily required. So example of this is library functions such as printf and gets. So gets, as you saw, is like truncated from current C library, but then still it's a function that is declared. So we'll talk about that. Gets and printf, as you can see over here, which was in like program.c, is essentially two functions that this program uses. Next, what are libraries? Yeah, so we discussed about it right now, but then to be in a very simple sense, what are libraries? Libraries are essentially a library of functions. So when you go to a normal library, you would probably go there to just get books and other things such as maybe read a newspaper, who knows. But then shared libraries, what you are doing is getting useful functions that you can reuse within your piece of code that you are writing. So examples for these are printf, scanf, fgets, etc. So glibc is the current standard for like most Linux platforms. And yes, that's about it for libraries. But then, why do we need libraries? So, as discussed before, abstraction. So, we don't need to know how printf works to print things to the terminal. So, we don't need to repeat mundane tasks such as printing things uh, over and over again. So, like this, you can like simplify code that you write. Then it reduces redundancy, as in we don't need every binary to have a copy of printf. So why are libraries called share libraries? So libraries are called share libraries in this context because like I only have one copy of libc.so.6 in my uh, computer, and all the programs that are dynamically linked to this file will be using this libc. So it simplifies things a lot. You just need a single file to be mapped into the memory of processes so that they can use the file. Then you have, yeah, so essentially there are also statically linked binaries which don't need these shared libraries because like we are linking them directly together uh, during compilation. So they also exist. But then, yeah, for this session, we'll be focusing on dynamically linked binaries, the ones which use shared libraries. So essentially, this is how it works. If we consider program P2, P1, and P3, suppose P3 requests a function gets which is essentially existing within glibc. Uh, when glibc, yeah, it the glibc is essentially mapped to the P3's memory, and then P3 can access functions that reside in this binary. Now, how do libraries interact with the world though? Syscalls. So this is how we move into the next topic. So you might have noticed that even though you can see that printf prints things to the terminal, you exactly don't know how it does it. So we'll be looking at syscalls, which kind of explain what it does. Okay, so yeah, this is essentially syscalls in a very simplistic sense. So suppose there is a small program in your running in your operating system. This guy, uh, who is like requesting for a file to be read. Suppose this program has already opened the file, so it will be in the open file list in the kernel. So the kernel just fetches the open file and details and then reads and then just gives the data to the program. So this is essentially the reads is called in the in the kernel. So yes, so this program does the read syscall and then it gets data from the file. That's about it. Simple as that. So syscalls are essentially calling kernel for requesting a service. So this guy requested for some bytes to be read in, and then he got the bytes. And then you have library functions do the same thing. So they call the kernel to do whatever they have to do. Uh, in example, puts calls the writes is called to put text onto the screen. So how do we actually ditch library functions and directly access the kernel functionalities though, such as syscall? So we can do that using the syscall instruction in assembly. So essentially the format is somewhat like this. Uh, so it's somewhat like syscall is a function which takes in arguments in RDI, RSI, RDX, which are registers. I hope you learned in the reverse engineering session. So you can have your first argument in RDI, second in RSI, third in RDX, and more arguments in registers such as R10, R12, which you can look it up in a specific syscall table, which is put out by Chromium, which is a pretty reliable source. There is an updated one in syscalls.pages.dev, which is also somewhere you can look into syscalls. So whatever number you are putting into RX, in RX I am putting OX3B. This is essentially the number of the syscall. So suppose we look into a library function. Okay, so let me just disassemble puts after running. Yeah, so yeah, this would be a library function. Somewhere along here there would be a syscall. Suppose the easiest function we could take is read. So yeah, so you can see here that libc read essentially has a syscall. So this library function is using syscall to communicate with the kernel and request for a specific service. So it's doing XOR EAX, so which essentially sets EAX to 0, which is the syscall number for read. Now we shall talk about the stack. So stack is essentially a data structure uh, which the program uses to manage memory. So, okay, so before that, we'll talk about what a function is. So in the source over here, so init is essentially a function, win is essentially a function, main is essentially a function. So what exactly defines a function? So function is something which uh, is a reference point which you can call to transfer control. So if you call win, it transfers control and goes through all of this functions, other functions, which calls printf, and in the end, you know, everything ends in a syscall most of the time, unless you are copying bytes in memory, which probably does not need kernel utilities. So yeah, in example, when is a function. So every function that is called will create its own stack frame. So I shall illustrate to you how that is working. So every program, while it starts in a section where the loader transfers control. It's at underscore start. So this is essentially where the program starts. After this, usually your program goes through libc start main, and then finally, after many function calls, it reaches your main function. That is how the program reaches your main. So which is this function which you write in a C program. So after reaching main, suppose you call init. So how does this look? Let us see. So inside main, when main is set up, main has its local variables such as command. This is a local variable that is declared inside the function. So this command will have its space reserved inside the stack frame of main. As I previously said, libc start main, call main, there is one more. So c start call main. So this is essentially from where from main is called. So whenever a function call is made, what you do is you push the address of the next instruction into the stack. So this is done through the call instruction. So what the call does is tracks where it needs to go back after the routine is completed. So if this is the stack frame of main, you can see that this return address would be of libc start call main and then plus some offset. This is because the main is called within some place within the function libc start call main. So yes, and here you can see that there would be space declared for the local variables. Suppose 20 bytes declared for our buffer, which is called command. So this is where command is. And since we don't have any other local variables, the main stack frame is restricted to this. We just have command. So yes, this comprises of the stack frame of main. There are other things which are also pushed, such as the previous stack pointer. So essentially, since stack is a data structure where you have a top and a bottom, and you keep pushing things onto the top, and the pointer to the top keeps changing. The pointer to the base of the stack usually does not change. But for implementations of function calls, there are a few differences that we'll talk about. So whenever I push something onto it, it essentially changes the top to this. Uh, issues. Hmm. Okay. So yeah, then top becomes this one instead of this. So whenever something's pushed, the top is changed to that, and the top is basically stored in a register called RSP. So the stack top is essentially an address which is saved inside RSP. So RSP will always point to the top of the stack, and the base of the stack is saved in RBP. So this is essentially the general layout of things. So currently inside main, before calling the function setup or init, we'll have the RBP that is pointing to here. Why that is the case is because after you have the return address being pushed, you'll have the setting up of the stack frame. So during that, RBP, the previous RBP will be pushed here. And the reason to that is because if RBP is saved, then you can essentially make sure that the previous stack frame is not lost. So if there was a stack frame here, suppose, and there was an RBP pointing here, after this function gets over, after main gets over, we need to return to this function, right? So it needs to know where exactly was RBP. So that is why RBP is stored over here. So yeah, so RBP points to this place. This should be other way around. Okay, and you'll have the RSP, which is point to this place. Suppose init is called, then init is called within some place inside of main. So as we saw over here, suppose I disassemble main, we can see that init is called at main plus 13. So the main plus 18, that is at this address, will get pushed onto the stack. So we'll have the address main plus 18 over here when init is called. So this is essentially what the uh, function prolog is like. So you set up the stack. First of all, you do a call instruction which pushes the return address. Then you set up the stack by pushing the RBP. After that, you make the new RBP point to the RSP, and you grow the stack by subtracting from RSP. That's it. Simple as that. So when you subtract from RSP, uh, this goes in a way such that this is the lower address and this is the higher address. So that is why you are subtracting from RSP. So stack grows from higher to lower address. That is another thing you can remember. All right, that should be too much info. So yeah, that was we were looking at init function. Now, uh, what exactly happens when you do get? No, before that, init was called, but how does it return? We can see that init does never has local variables. So let us just finish this. So when init is called and init returns, it pops this thing from the stack so that it can return to that address. So what exactly could be the instruction? And we can see that it's the ret instruction. So it's an instruction that pops the return address from the stack and jumps to it. So that's how the program knows where to return to because it's saved in the stack. So after init, it just uh, returns, and then you can go to main. You can completely ignore whatever was happening over here. And main can just continue its execution and call other functions. Pretty simple. So this is how function call works in x86, which is the architecture we are focusing on currently. Now, after this, uh, we can see why stack is a target for exploitation. So local variables are stored in the stack. As I mentioned right now, uh, over here, the command is stored in the stack. So if anything wrong goes with the command, it affects RBP, which is saved, as well as the return address. The return address decides where we return where we return to after a function call. So what exactly do we control? We can see. Another thing is you would think where global variables are stored though. So global variables are stored in the data section of the binary. So if you can see, hmm, right, yeah, suppose, so if you have a fixed static variable, it would be declared over here. Um, yeah, and if it's not the case, it would be declared at OX 40. Yeah, over here. So this is essentially the a place where your global variables which change are declared. This address can usually be observed if you uh, get the mappings of the program, and yeah, that can be very easily done through GDB. Then yeah, now we shall move on with the demo, which is of Stack Overflow, and using that Stack Overflow to do a red to win. So with everything that we understood from now until now, so we have a command over here, and then we have the gets function. So a peculiarity with the gets function is that it reads in as much bytes as the user inputs up until a new line. So that is a pretty bad thing, considering how you can see that the space that you reserved for command is only OX20 bytes, or only 20 bytes. So that means if you keep writing uh, something over here, such as a, and you write past 20, you would end up reaching RBP at some point. And finally, after reaching the RBP, you would corrupt the return address. So you can essentially write whatever you want over here. So if the binary is having an address such as, if we see a function such as win, this function is there. So this has a static address in this binary because of certain mitigations being disabled. So if that's the case, we can just put that address over here, as in win over here, and then our program should essentially return to this function, which is win, right after it returns from main. So this is essentially the concept of red to win. So you are returning from a function such as maybe main to a function of your choice, which in here is win. So that's how red to win works. So yes, we shall try solving this challenge now. So we shall briefly look into the source code. So in it, so this just sets up buffering for the challenge. Uh, you guys can look it up if you want, but mostly this just disables buffering so that uh, things can be displayed in a proper manner when required. This is essential for most challenges, as the due to buffering requirements, we might not be able to solve certain challenges. So this is just to make things easier. Then yeah, suppose we see win function, we essentially are printing out congratulations, F society salutes you, uh, for people who get that reference. Then it opens flag.txt in read only, and if flag is not found, it exits, and it reads the flag using fgets, and then it prints the flag using printf. Simple enough. What we want from a CTF challenge is essentially the flag. So if we can somehow call this win function, we win. So yeah, first of all, we the program would call main, after it calls start libc, start call main, everything like that, and then it would call init. The main would call init, and then you have this command declaration, which is of 20 bytes. So another peculiarity about mm, x86 and like the memory is that you stack is 16 byte aligned. So whatever things that you drop, such as the size of the variables, if it's 20, it's always aligned to 16 bytes. So if you have 20 over here, uh, that buffer size should essentially be uh, rounded up to 16 bytes. So it'll probably be 32. Then yeah, we can look at the source again. Yeah, it prints a lot of things, which is probably not necessary. Now, what it does here is interesting. So, as I mentioned, gets allows us to take in as much input as we want. So we can use this to overflow this buffer, and then make sure that this return is essentially going to win. So let's try that. So inside the main function, we can see that the space that is made is essentially 20 in hex. As I said, it is 32. So if you convert 20 from hex to uh, decimal, it would be 32. So then you have, uh, yeah, you move ex20, you call init. After that, uh, it does the printing of things. Yeah, which is interesting because uh, we saw printf over here and it's puts over here. Uh, that's a thing that you can figure it out for yourself, I guess. Pretty interesting. You can look it up. After that, it calls printf, uh, which is for this, and then finally it calls gets. So this is essentially what we want. So where does it uh, get its input into? So as I mentioned, the first argument is of gets is gonna be Rx. So where is Rx? Let's check where Rx comes from. It's RBP minus OX20. So it's OX20 from the RBP. So we can understand that um, if this is the return address and this is the RBP, you would have OX20 bytes that you would need to write to reach the RBP. So that is essentially what this means. So when you do gets, you now know the buffer size. You know how much you need to write to reach the RBP. Corrupting the RBP is probably not of that much use right now. So we shall focus on return. So yeah, we'll have gets, and then it is getting its input to RBP minus OX20. So we shall start scripting for this. So yeah, don't get intimidated by this. You can just use spawn template to get you this exploit script, which is essentially a simple startup script that you can use if you are a beginner to binary exploitation challenges. So yeah, uh, we can, yeah, since we identified how much is the buffer size, we can see that it's OX20, and then that much is what we need to write initially. So beyond that, we would start corrupting RBP. So how much bytes is RBP though? You guys probably learned in the reverse engineering session that it's 8. So you will have to write 8 more bytes to account for RBP. So let us just write 8 more bytes. After that, you would have the return address. So I am hoping you learned endians in the reverse engineering session. If you didn't, I'll just explain it in a very quick manner. So endians essentially mean the organization of data in memory. So if you have something like A, B, C, D, string, then in big endian it would be written as from higher address to lower address. But in little endian, it would be from lower address to higher address, as in this would be 0, 1, 2, 3, and this would be reverse in big endian. This would be little, this would be big. So same case for numbers. So if you see numbers in such as OX 20, 30, suppose this is a number. In little endian, you would have it this be 0, then 1, and then in big endian this would be 0 and 1, like this. So that's how the indexing goes for the bytes. So this would be in the 0th position, and then this would be in the first position. For big, this would be in the 0th position, and this would be in the first position. That's it. Very simple. So to do this, Pawn Tools has a helper function which is called P64, which you can use to write addresses to pack your data into the endian of your choice, which is by default little endian. So yeah, I'm gonna be packing my data, which is win in little endian. So we are trying to, what we are doing is we are trying to write the address of win over uh, the return address. So let's see how this goes. Oh, I missed a byte over here. Oh, yeah, I also needed to send this. There you go. So yeah, and we got error opening flag.txt. So yeah, I haven't created the flag. Let's just create the flag. Flag. Yeah. So now when we run it, you can see the flag is being printed. So yeah, that's about it for the relative insolence. So one another fact that you might want to know is the alignment. So I said everything in stack is essentially 16-bit aligned, no 16 byte aligned. So this would probably cause issues when you are trying to return to functions in a direct manner. So if you're like directly returning to some function which uses uh, complicated other complicated functions, it's probably going to use functions that assume instructions that assume the stack is 16 byte aligned. So for that, what you can do is just have a ret again, and yeah, that should essentially fix things up. Why does it fix things up? You can notice. So when you return, if you see, um, I shall break at this, and I will say, okay, wait, let it be. Mm, yeah. So yeah, I'm at breakpoint two. So we are just showing the stack state. RSP. So this is how the stack looks. So yeah, and if we print out RBP, we can see that RBP is over here, and this would be our return address which we overwrite. So yeah, so this, if you see the address of that which we just saw, it is CE and then 8. So sometimes when you return to functions with this, the stack won't be aligned, as in uh, the stack is when aligned whenever this last nibble is 0. So if the stack is not aligned, it would just crash because it assumes, and you assumes the stack is aligned and uses instructions such as, in example, you can have the move apps instruction, which essentially assumes the stack is like 16 byte aligned, which would mess things up for you and it would just check out. So that is why you have to sometimes align the stack, or you have to be lucky to use the functions that are not causing issues like this, or you'll have the initial buffer itself aligning the stack for you, which is a common thing. So yes, this is how a standard right to win challenge works. I am hoping you understood everything in a pretty uh, good detail. So yeah, that is it for the demo, and thank you for attending the session. If there is any interesting questions, we shall go through it. Okay, so since we can't find any interesting questions over here, if you have any doubt, you can just ping in the Discord and it shall be answered. Thank you for attending the session and hope you understood what binary exploitation is. And we shall be looking into more depth tomorrow. Thank you.